thanks for the kind introduction. I'm very happy to be here, virtually here, and present my work, our work in the lab to you guys and visit Cornell. So this is a work on LSM trees. Specifically, it's a prelude to robust LSM trees. So we have been working on tuning LSM trees for a few years now, and now we are actually moving into tuning LSM trees robustly, and I will say a few things about that, but I will mostly focus on our prior work on tuning and understanding the how the internals of LSM tree really works. So as Emmanuel briefly said, LSM trees are actually the backbone of many different systems. Today, here I have just a few names that are very popular that many of you have probably already seen. Big names like Bigtable, HBase, RocksDB, LevelDB, Cassandra, and other newer companies are actually using under the hood, either for their main data storage engine or as an experimental data storage engine. They use LSM trees. The reason for that is because LSM trees essentially offer fast writes, very fast writes, while they're also offering competitive reads, and they can offer good space utilization. If you go over the DBLP data over the last few years, you'll see an upward trend in papers about LSM trees. This increasing trend really started in 2006 with Bigtable, but then many different systems have been using LSM trees, and this is exactly because of the three reasons I mentioned: very efficient writes, competitive reads, and good tunability and space utilization. Now, one more facet of the problem that we're interested in is what happens to the trade-offs that these systems are actually navigating when we're moving things into the cloud. So cloud data management is essentially the name of the game today in many different aspects. And here we would like to see some of the challenges. Sorry, quick question. Is it possible to mute, because I get some noises back from my headphones and it's a little bit confusing, and we can unmute, of course, if there's any question down the line.
All right,
if that's fine. Okay, thanks. Again, feel free to interrupt me. This is not meant to mute the audience, just so I don't hear things that a little bit confuse me while I'm speaking. So, okay, so what are the cloud data management challenges, right? So unpredictability is the most important one. Essentially, we don't have exact knowledge and full control of what's going to happen with respect to workloads, access patterns, ingestion rates, and so on. But also, the underlying hardware might be different, like compute, memory, storage. The availability of the hardware to us might vary as we are executing our workloads, or as we are actually requesting specific resources. If we don't make a hard request and we make soft requests, we may get different hardware than what we're expecting. And this overall leads to a situation where small is big. What do I mean is that even if you have small data sizes, when you are deploying in the cloud, and you have multiple instances, this multiplies. When you have small overheads or small benefits from an approach, this will multiply because of the cloud deployment, and this will impact energy and monetary costs. So these are the challenges that cloud deployment of data management solutions have, and here we're mostly focusing on unpredictability, specifically unpredictability in terms of the availability and the type of resources, the incoming workload, and the assumptions that we have over the application and what we can or we should do with our data, specifically about data deletion and data retention. So this unpredictability in any of those facets essentially hurts tuning and design decisions. Now, with respect to LSM trees, again, the design trade-off, the space that we are navigating has to do with writes, reads, and space utilization. And in order to address any such challenges, we need to think about tuning and about compaction. So I will explain what the compaction operation is, which is at the heart of LSM trees. And this is going to be the focus of our discussion today. What does compaction mean? How does it behave? What are the different options, and when we should use each of the options? So with the rest of the talk, I will start with an LSM trees primer, just to make sure that we're all on the same page about what an LSM tree is doing. And then I'll mostly focus on these two pieces of work here, which is the LSM compaction design space. And then depending on the time that we have, I will briefly talk about the impact of delete requirements on the application and regulatory side, how do we need to take this and make them actionable items for the system side? And if we have more time, we can discuss a few more facets of making LSM trees robust, but mostly the first two will be the topic of today's talk. So let me start with an LSM trees primer. And after that, I will pause, for any questions and so on. But of course, if there's anything that cannot wait, feel free to interrupt me. All right. So, okay. So LSM-tree based key value stores, what do they do? So essentially, we're not only storing semi-structured and document data with LSM trees today. We can also store relational data. And in a nutshell, the way we are doing that is that we are using the primary key as the key of the key value store, and then the remaining part of the row becomes the value. And then using this key value representation of data, we can store relational data without any problem. We can also store indexes by using the specific columns that we're interested in as keys, and then values will be, of course, the primary keys that we're interested in. So essentially, LSM trees are also used for relational data today, so it makes it as essentially a widespread standard way of storing data under the hood. Now, what is the LSM tree doing really in terms of moving and storing data? How does it work? So for the remainder of this primer, I will think of the key values as a key which is an integer and the value which is an arbitrary number of bytes, which we don't necessarily know what is inside. So what happens is that we want to first optimize for ingestion. That was the main motivation for LSM tree. So here on this slide, on the left-hand side, we have structures in memory, and on the right-hand side, structures on the disk. So as key value pairs being ingested into our database, they are collected into a buffer, and when the buffer gets full, we sort the buffer and we write it to the disk as a sorted run. And here, this sorted run is in level 1. That's the L1 next to sorted run. So this has nothing to do with the caches. It has to do with the notation of the LSM tree. So when the buffer gets full again, we sort it and we write it on the disk. And now that we see that we have these two sorted runs that they go above a threshold that this dashed line indicates, we have to sort merge those two runs and move them to the next level because they go above the threshold. Right, so we keep doing this sort merge iteratively of files with equal sizes, and we end up on a steady state. We end up on a tree that has a logarithmic number of levels, logarithmic to the total number of data that were ever inserted, each of which has exponentially increasing size based on a size ratio t, which is essentially how many sorted runs we are merging every time that we are pushing things from one level to the other level. Right, so if we are at this steady state here, notice that we have the thresholds in level 2 and level 3. If another buffer comes in memory and gets full, and then we sort it and we write it on the disk, and then this level 1 goes above the threshold, right? We'll have to push this data to level 2, and then if level 2 goes above the threshold, we'll have to push this whole data to level 3, and then we will essentially cause a cascade of compactions across the whole tree. So this leads to a burst of IOs and prolonged write stores because the latest write has to wait for the whole compaction to finish across the whole tree, which is undesirable for making actually our performance, let's say, robust or predictable. So instead, state-of-the-art systems, what they do is that they actually physically store every level of the tree. Remember, every level has sorted, is essentially a sorted run based on the key of the key value pairs, right? So they physically store these sorted runs as separate contiguous files, right? So essentially, every little blue box here is a separate physical file. However, the first blue box of level 2 has smaller values, smaller keys than the second blue box of level 3, and so on for the other levels. So now when the buffer gets full, we push the buffer to the first level, and if it goes above the threshold, we don't compact the whole level. Rather, we take one file with some policy, we take one of those files, and we push it to the next level by merging this file only with the overlapping files of the next level. In this case, it might be only one file, let's say, right? So we merge those two files, and replace this one file with the two new files that were the result of the compaction, which is termed partial compaction. Okay, and we will keep doing that. If the next level gets full at some point, we will select just one file with some algorithm, with some decision process, and then we will actually push this file to and merge it only with the overlapping files on the next level. So this amortizes the compaction cost and makes essentially no insertion a very expensive one, while on average, the behavior is about the same. All right, so what happens if I want to query an LSM tree, right? If I want to query an LSM tree, remember that everything on the right-hand side is sorted runs, is in the form of sorted runs on the disk. So in order to avoid doing a binary search on the disk, what we have is the so-called fence pointers. You can think of them as zone maps as well. It's essentially the smallest key per page. It's stored into a map in memory, and instead of doing a binary search on disk, we're performing a binary search on the in-memory helper data structure, and then we go directly to the page that. We'll go directly to the page that we are looking for. Now, notice that when we go to the appropriate page of every level, if we are looking for a specific key, we might or might not find the specific key. We will definitely find the page that would contain the key if the key existed in that level. So essentially, in that respect, we will do one IO per level for every point query, which is not that bad, because remember, the number of levels is logarithmic with respect to the data size. So log n IOs for a lookup is not actually that much than what a bit tree would do, right? If, of course, we don't have caching effects. Right? In order to actually, however, make this more efficient, because in this case, we only had 5 in the last level, and we didn't need to do any of the searching in the other levels. They were empty in terms of key 5. We also use Bloom filters. So Bloom filters are probabilistic data structures that essentially allows us to completely skip a set by searching on this set if it does not contain the value we're looking for. Now, the Bloom filters might have true positives, might have true negatives, right? Which is the first case that it says no and it's not there. But it might also have false positives, in which case it will say, yes, 5 is in level 2, right? But we'll just go to level 2 to not find anything. And it can also have true positives, where essentially it will say yes, and then I will go and find a 5. Essentially, the problem here, like the benefit is from the true negatives, the blue axis, that actually allow us to skip entirely some axes on the disk, and let's say the wasted memory is coming from the false positives that even though we have a Bloom filter, we have to go still to disk to verify whether the key that we're looking for exists. So however, the probability of a false positive is tunable, and essentially this allows us for the first way of making our LSMs very tunable and exchange memory space for read performance, where we can actually allocate more memory to our Bloom filters and make it more accurate with respect to false positives, essentially trading off memory space for read cost. And on the other hand, LSM-trees are very tunable with respect to how aggressively we merge. And essentially we can perform more merging, leading to fewer runs. And if we have more merging, we'll have higher update cost because we will be merging more frequently or more aggressively. But this will come at the benefit of having fewer sorted runs to search, which means that the read cost would be smaller. Sorry. So efficiently, reads will be more efficient. All right. So, okay, let me take a pause. So this was the LSM-trees primer. Essentially, this is state-of-the-art things, nothing new here. I would like to see if you have any questions, and if not, I can move on with the next topic of today's talk.
Does anyone have? Oops, that's that.
Sorry, that was me. My name is Athanassoulis. I'm from the University of Pittsburgh. Great to attend this talk, but the question was answered right away with the Bloom filters. I had a question about the fence pointers, but you rectified it. Thank you.
All right, sounds great. Okay, so let me move on now to LSM compaction design space, right? So I talked already a little bit about compaction. So what is compaction? It's the process that happens under the hood to reorganize the data in order to maintain this nice structure, this nice exponentially growing structure. Compaction does not affect only insertion or write performance. It affects a number of different metrics, including space amplification, write performance, lookup performance, write amplification, scan performance, and delete performance. And in most cases today, compaction is being treated kind of as a black box, and it's not clear if we change the workload or if we change some of the aspects of the tuning, how does that affect, and we vary the compaction strategy, how does that affect the performance that we will measure? So in this work, we try to understand really what are the different options of compaction, which up until now, I just quickly said, okay, we compact data. But essentially, there are multiple different options, and we like to see what do they mean and how do they impact the remaining of the metrics of the system. So we would like to build a roadmap to pick compactions and a way to answer complex design questions, and we do this by opening the black box and learning from more than 2,000 experiments on RocksDB, one of the state-of-the-art systems, with different compaction strategies that we will explain and analyze in the next few minutes. Okay, as a very short reminder, the compaction essentially is either a full compaction between levels, or it can be a partial compaction between files of each level. And we'll see a few more options down the line. So in order to understand really what is the big deal with compaction and how many options can we really have, we actually asked 4 questions that have to be answered every time we're performing or we're attempting a compaction. The first question is how to organize the data on the device after the compaction. The second one is how much data to move at every time we perform a compaction. The third one is which data blocks to select. If I can move any data block from different levels, which one should I select? Which one makes sense to select to move in the compaction? And the fourth one is when to reorganize the data layout. So what would be the reason that I am triggering a compaction? And essentially, we codify those as data layout, compaction granularity, data movement policy, and the compaction trigger. Okay, so let's see what are the options. So data layout, so numbers of run per level. So up until now, in more classical papers about LSM-trees, you'll see that they talk about the so-called leveling compaction and tiering compaction. The leveling compaction guarantees that every level has a single sorted run. So whenever you want to perform a search, you go to this one level and you simply do one search in the sorted run. However, in order to maintain one sorted run per level, this means that every time you push something to that sorted run, you really have to actively merge it with whatever is there. So the other extreme is tiering, which maintains a number of sorted runs. And every time we push something to a level, we just keep it there as a separate sorted run until we accumulate a number of them. And then we at some point, we have to merge all of those. So tiering and leveling are the two extremes. But the last few years, we have seen that there is also a lot of intermediate hybrids. Most prominently, the intermediate hybrids are the ones that essentially alternate the choice between tiering and leveling in different levels. The two most frequent choices is one leveling and L leveling. Essentially, one leveling says that we're going to have tiering in the first level and going to have leveling in all of the other levels. And L leveling is the other way around. We have tiering in all of the levels except the last one. And leveling in the last one. So tiering and leveling is a way to actually tune between reading and writing, because if you are having a lot of read queries, you want to have fewer sorted runs because every sorted run leads to a search. If you have a lot of write queries, you want to have more sorted runs because every time you merge those, you're actually delaying a future write. So here we can navigate this trade-off by actually making a choice about the data layout. Now, the second decision is about compaction granularity. So how much data to move per compaction. This is tightly related with essentially some of the previous decisions, and the options are either entire levels. So we either merge one full level with the next level, or files from level. So we select one file from level I and we compact it with the overlapping files of level I+1. Or we simply merge files within a sorted run when we have a condition met in order to finalize and create one sorted run at that level if we have tiering. This is only good for tiering. Now, the third question is about data movement policy. So which data to compact, and that's where the fun begins, because once you have partial compaction in your system, now you can make any decision about which files to compact. And there's a lot of options. For example, some of the common ones is the file with a minimum overlap with the parent level. Parent being the bigger level on the bottom. The coldest file, the file that hasn't received any accesses anytime recently. The file with the most tombstones. We'll see a little bit later on. A tombstone is a special key value that deletes an existing key, or a round robin that requires no metadata management, simply a round robin decision about which files to push. The fourth question is compaction trigger, which is when to invoke the compaction routine. And essentially, there's a number of options varying from level saturation, essentially saying that if we have a threshold size, and if we exceed this size, then I need to do something with that specific level. Or it can be a number of sorted runs. Then maybe the threshold is, in this case, is described in terms of sorted runs and not in terms of data size. So now if we exceed this number of sorted runs, we have to push. A third one is age of a file. So if a file is old enough, then it might contain older metadata, older tombstones, older updates that have to be propagated. So maybe this is a way to choose files. Or space amplification, essentially if we see that our system has a lot of duplicates and a lot of its space is actually occupied by invalid data, then we want to invoke a compaction to reduce the space amplification. So with these 4 questions, we essentially answer or can essentially design any compaction algorithm out in the wild today, or at least that's our claim. Hopefully, most of the algorithms can be categorized under this classification, but maybe there will be some new ideas down the line that will actually open a few more design dimensions, or maybe a few more options in some of the design dimensions that we mentioned today. But in our paper from VLDB this year, like this past summer, we have classified a number of different papers and approaches with respect to what options they are actually using with respect to any of the 4 questions. And they have this table, but you are welcome to go to the paper and see in detail all the analysis that we have about what system is doing which options. I'm not going to focus on the table today. So having all this infrastructure of modeling the design space, we said, okay, let's try to really now compare different options in a directly comparable manner. So we set out to perform an experimental study where we vary the options. We vary the options for every primitive to get 10 state-of-the-art compaction strategies, and then we vary the workload composition and data distribution when we are performing experiments to report on the key metrics on compaction strategies. So we mostly vary the fraction of its query type, and by query type I refer to empty lookups, non-empty lookups, point, range queries, and updates. And we also varied the data distribution between uniform and Zipfian. And we also varied LSM tuning, the classical LSM tuning questions, which I'm not focusing a lot today, but every LSM tree comes with decisions about its size ratio, its memory buffer, its Bloom filter, memory allocation, that are essentially tuning knobs that affect the performance of the LSM tree. So overall, we collected 612 metrics for each one of our 2,000 experiments, and we're going to report a summary, a very, summarized version of what we observed out of all these experiments. So let me first start by the 10 state-of-the-art compaction strategies that we used that are actually used by real systems today. So the first one is called full leveling, or for short, it's full. And what it does is essentially it performs full leveling between entire levels. There's no data movement policy, and the trigger is level saturation or level size. This is the classical LSM merging presented in the first papers that were out there, and it is essentially trying to optimize for it queries. Now, the next group of policies, compaction policies, we name them LO+1 and LO+2, which stands for least overlapping parent or least overlapping grandparent. The idea here is that we have a partial leveling strategy so the granularity is files, and every time we select to move a file based on the compaction trigger, which is the size of the level, the saturation of the level, the decision of which file to push is made upon the overlap between the file, between any of the files of the level which is above the threshold size and the next level, or two levels ahead with the least overlapping grandparent. The rationale here is that by this way, if we really manage to find a file that has zero overlap, we will not overwrite anything. We will simply move some metadata and completely avoid merging. Essentially, we would reduce or minimize write amplification. This is the rationale of these two systems. The next group of systems are called old and round robin. Essentially, it's still a partial leveling approach where the data movement decision is not being made based on the overlap, but based on the coldest file, oldest file, or a round robin, where the idea here is that I want to help read queries. So if I move the coldest file, I will keep the warm files higher in the tree, which will be more accessible and will be still maintained in the buffer cache or the block cache, and it will help read queries. And more or less, this also is the idea for the oldest file, while for the round robin is simply to avoid any metadata handling. Now, the next two, which I'm gonna come back in the end of the talk when we're talking about deletes, the next two are about deletes essentially. And here, the idea is that deletes are happening out of place by inserting a new entry, which is a special tombstone entry that invalidates a specific key, the value of a specific key. So if we have such tombstones in the tree, we might want to do something based on how many tombstones we're having in the tree, because they actually create invalid data that propagate throughout the tree. So the two policies here, one is most tombstones, the TSD that comes with the density of tombstones, and TSA, which is the age of tombstones, is moving the files with the oldest tombstones that have an expired time threshold, as we'll introduce later on. For both of them, the trigger is also the same metric. So the density and the age of the tombstones is the trigger. But if we don't go above a threshold, as a secondary trigger, we have the size of the tree, the level saturation, the size of the level, that is. Now, the next one is tiering. So tiering. So tiering is essentially a very different approach that optimizes for write queries, and it does not have data movement because we actually are merging all of the files of a specific level, all of the sorted drafts of a specific level, and the compaction trigger is either the number of sorted drafts or the special amplification, as it is actually done by RocksDB, one of the default policies of RocksDB. Finally, last but not least, we have one leveling, which is a hybrid approach that has tiering on the top, leveling on the bottom. The data movement is classical least overlapping parent for the leveling cases, and no data movement policy needed for the tiering first level. And the granularity is the whole number of sorted drafts for the first level and specific partial files on the remaining of the levels. And the trigger again is the sorted drafts and the level saturation. Okay, so this hybrid essentially absorbs inserts and wants to be reasonably write optimized, but gradually optimizes for each as we are performing more aggressive merging in the remaining of the levels after level 1. So after this brief discussion of the 10 compaction strategies, I'll present some of the key results out of our experimental analysis. So first, it really helps, it really pays off to actually perform compaction in smaller granularities. So here in this figure, we see this is the full leveling that on the left-hand side, and on the y-axis we have the total data movement, reads and writes. So the full leveling performs a lot of reads and writes because of the compaction of the entire levels, even if we don't need to merge the whole level. Every partial leveling strategy performs significantly less compaction, up 45% or more reduced reads and writes on our devices that actually help better exploit the bandwidth of the devices, and if it's an SSD, for example, to wear a device slower, right? Of course, if we go to tiering, because tiering merges even less frequently, the overall data movement is significantly lower to 75% with respect to full leveling. And notice this green line, which is this is the actual data size. So this is for 1 gigabyte. This is the total data movement while we're performing our workload analysis. And then one leveling on the right-hand side is actually somewhere in between tiering and the remaining of partial leveling strategies, as we would expect. So it's kind of the best of both worlds, but of course it cannot minimize write amplification and data movement as much as tiering. Now we focus on another metric, which is the Tailright latency. So why tiering is the approach that actually moves fewer data around. This comes at a cost, and the cost is that we have these expensive compactions, like cascaded compactions, that we merge multiple levels and multiple files from multiple levels in one go, making the Tailright latency significantly higher than any of the other policy, specifically than any of the classical partial leveling policies, 5x or worse. Right. So essentially, if you really care about stability of performance, pure tiering, which was initially marketed as the right friendly way to go, is not necessarily your design of choice. Now we then shifted our attention towards read queries. So here we vary on the x-axis the proportion of empty point lookups. So on the left-hand side, zero empty point means that every query actually is fetching some existing data, and 100% empty point lookups means that no query is requesting existing data, right? What we see here in the point lookup latency graph on the y-axis is that, first of all, the one leveling dominates all of the other approaches, while the tiering becomes significantly worse, specifically for some empty point lookups. And also we observe a U-shape. So let's first discuss why one leveling is better. So one leveling is better mostly because of caching. So what do I mean by that? Every time we perform a partial compaction, every time there's a buffer flash in a partial compaction, there is a cascading compaction in all of the levels, but only of one file. So essentially, we put one file from the first level, we put to the second, and then one file of the second, we put to the third, one file of the third, we put to the fourth, and so on and so forth. This, unfortunately, creates a pattern that essentially evicts many of the warm pages from the buffer pool, or block cache, as it's called in LSM trees. Essentially, we can only have most of the time we have in the buffer pool only pages from the last level, and any other level is doomed because of this compaction, of this cascading nature of compactions. On the other hand, for one leveling, the compactions of the first level are performed lazily, so they don't create this cascading pattern, essentially being able to maintain all of the hot pages in the buffer for longer time. So that's exactly why this benefit comes with respect to one leveling, with respect to reading, and when we compare with any of the other approaches. And of course, tiering is much worse. This is the red line. Tiering is much worse because every time we're performing a query, we have to search many more sorted runs throughout the tree because of the lazy merging. So we have to read so many more sorted runs that there's no way to actually win unless we find what we're looking for very early, which is the case for zero empty point lookup, so 100% existing queries. Now the next question is why the reverse U-shape. This is a little bit more subtle, but essentially, if you have an empty query, what you are doing is that you'll be using all of the Bloom filters to make sure that you discard your accesses in all of the files. If you have a non-empty query, you'll be using all the indexing metadata in order to find the pages that contain the values you are looking for. And we observe here, by plotting the index page block miss count and the filter block miss count for different alpha values, 0, 0.4, and 1, we observe that for alpha equals 0, we have a lot of index block misses, which actually makes our cost higher. While for alpha equals to 1, we actually have a lot of Bloom filter cache miss block misses. I mean, it's always the case, but specifically for alpha equals to 1, typically this number is higher. So essentially, we have to pay more unnecessary accesses to indexes or to Bloom filters in the two extremes, while the accesses are more balanced in the middle, which is why we have this reversed U shape in terms of performance. Now, all of those were with uniform data distribution. When we switch to Zipfian, things are a little bit different, and the rationale is very simple. All the useful data fit in the cache that we have, a very small cache that we have. So essentially, except for the difference in nature of the cascading compactions that still happens for the one leveling, there's no significant difference between the other approaches, because whatever data we're interested in, they all fit in the cache, in the block cache. Our next experiment is about update intensive versus unique insert intensive. So this is a subtle point. So many of the workloads have unique inserts. So every insert is a new key. There's no overlapping key. So essentially, when we are merging, we do not discard any older values, right? But many other workloads have actually a lot of updates on the same key. Imagine that this is, for example, change of location, right? So with the same ID, we have a new location. So we really want to update the location. So here on the x-axis, we vary the update to insert ratio. So update to insert ratio 0 means that we have only unique inserts. Update to insert ratio 8 means that for every unique insert, we get 8 updates. And what we show here is what is the right amplification in this first graph for all the different approaches. And what we see is that as we are actually increasing the update ratio, there's a huge benefit for tiering. So this makes tiering, again, it brings back some of the good things for tiering, which is you don't need to merge useless data. You collect a lot of sorted runs, and then you merge all of them in one go. So you can really discard all of the useless data in this one go. So this actually makes it much more efficient in terms of rate amplification, makes tiering much more efficient in terms of rate amplification, while the next best thing here is least overlapping parent, grandparent, and all of the remaining approaches are actually stuck together in the same behavior. Another facet of this experiment is that by having more and more updates, we're actually making tiering better in terms of tail compaction latency, right? So you remember this number was very high in tiering in the classical simple workload, which made it a bad use case, a bad example for requiring predictability in your write performance. In fact, if we have a lot of updates, then actually tiering becomes much more stable, and the only question about tiering now remains the read performance. Okay, so we have more experiments in the paper, and you are willing to go over them in detail. There's a lot of observations, more subtle observations. I think we have more than 15 observations in the paper. But essentially, these are the numbers I would like to share with you today, along with one more high-level comment that the classical tuning decisions about things like size ratio, membuff size, block size, Bloom filter memory allocation, all of those didn't affect the relative behavior of compaction strategies. So essentially, we varied all of those, but whatever observations we had for the relative behavior of different compaction strategies remained the same as we varied their tuning. So essentially, there's no real interplay. It's kind of orthogonal. The classical tuning and the compaction decision are kind of orthogonal decisions for an LSM tree. Okay, so with that, I would like to conclude this part of the talk and maybe pause to see if you guys have any questions or thoughts or feedback or any other ideas you'd like to share.
Hi, there's been a lot of recent work on learned index structures, right? I've seen a couple papers where they try and replace the Bloom filter or the range index part of the LSM tree with some kind of learned index over the data. So how does that affect, I know you just mentioned that it's the tuning strategies are kind of orthogonal to the compaction strategies, but if you were to greatly improve those areas, would that affect the compaction strategies in any way?
So that's an interesting question. So how how does learned indexes come into play with LSM-trees in general, I would say. Let me start with that. So learned indexes is a very exciting direction that essentially makes some assumptions that we have all the data and the data is sorted. At least that was the early learned indexes papers. Now we have some more dynamic papers as well. And that's why some of the ideas are a very good fit for LSM-trees. For example, we don't even need to have the fence pointers if we have a smart way of searching over our already sorted files. For every sorted file, it's already there. It's already a sorted file. It's already mutable. We might as well use some of the great learned index ideas to search on that quickly. In fact, there is a paper from University of Wisconsin that actually does exactly that. At least one first approach of doing exactly that. But I would go, as far as we can start by a very simple approach. We can do extrapolation searching or interpolation search. It has both names, I think. So you can use that. Essentially, you don't need to store metadata. You just need to store some information for your distribution of the data, or you can use your favorite, learned search algorithm, learned index algorithm to search. So you can definitely do this. With respect to, I don't see how this changes the need of a compaction. We need to compact data because we need to have a limited number, a limit in the number of sorted segments that we search in. So this number of sorted segments that we search in has to be limited. So this compaction essentially is simply short merging key value pairs, which has to happen. But the metadata on top of those can definitely use and exploit all the nice learned index ideas. With respect to the Bloom filters, there are also a lot of work. It's not only Bloom filters today. We have ideas that are using cuckoo-based filtering. We have ideas that are using try-based filtering from excellent work from CMU, the surf approach, and all of them, can work. All of them actually bring some new design parameters on the table. Essentially, I don't think there's a clear winner for every single one of them, but there are different workloads that a different option would be better. And there's another paper called Rosetta from Harvard, which actually really explores which type of queries and which type of memory availability you can use, like for every type of query and for every memory availability, which filter you should use instead of Bloom filters. Which is and all of those like excellent piece of work that can be added into the design decision of the whole LSM tree. It doesn't really affect the compaction a lot. The only thing that still remains an open question is whether we can reduce the cost of building this metadata, for example, the Bloom filters, at compaction time. Because as you can imagine, every time we compact, we actually have to build the new Bloom filter for that specific level. This is not deemed to be as an expensive cost in general, but as the storage becomes faster, as we are moving from SSDs to non-volatile memories, the cost of hashing something might be non-trivial. So there will be opportunities for further improvement down the line, I think, over there. I hope I touched upon the questions you had with this answer. Great. Any other points? Okay, so I know that you probably have some other meetings down the line in a few minutes, so I would like to take just a few minutes to talk about the impact of delete requirements, because this is something that I'm very invested in. I think it's very important to understand how regulations change the way we build systems. And in fact, we have been actually publishing also a new paper that I don't talk about today, but that talks about the needs to update SQL to make it more expressive for such requirements. But today we'd like to speak for the system side of things and what does that mean for LSM trees. So let me quickly motivate this work. Essentially, we see a lot of production systems that actually face challenges with deletions. For example, ZPDB, it's part of a Facebook study. It's a system that is used in Facebook, manages 20, this is from 2 years ago, so manages 25 million deletions per day. So they have to do something with those, and they actually cause performance problems. And we have thousands of merge operations due to delete every short amount of time, but actually in some cases holds the performance of the system, but also comes with other challenges. By the way, deletion is not only coming from the user. So deletion can come from an internal operation like dropping a table or migrating data between different nodes and on our distributed setting. And essentially, we want to do the migration at the logical level, so we don't care about when the data was going to be exactly moved and how, which means that there's going to be logical deletions under the table. So also deletions happen during cleanup, data cleanup, garbage collection, and so on. But even more importantly, I would say than that, deletions are somehow enforced by regulation that wants to support the privacy of the users. So there's a lot of regulations enacted as laws the last few years, GDPR in Europe, CCP in California, VCPDA in Virginia, and essentially they all outline the right to deletion or the right to be forgotten, if you want. And essentially, if you try to codify what they say in English and to convert it into queries, into delete queries, they want to support on-demand deletion with guarantees about when the delete is going to be permanent on the data, and they want to support delete or rolling deletion, so essentially getting rid of data every X days, so that sensitive private data do not stay in a data provider forever. So essentially, we'll focus on the first one for this talk, but we have done work on both of them, where we want, when the user says delete my data please now, we want to say, even though we don't delete the data immediately, we want to provide guarantees as to when the data will be deleted. Going back to the discussion about LSM trees, this deletion today happens with a tombstone, a specific key value store that has a tombstone flag, which if it is set, this key value entry will essentially invalidate any previous key that exists in the system. And in order to make it smooth in the system, what really happens is that we have a flag. Every key value entry has a flag right after the key. If this flag is set, then this entry is essentially a tombstone. The way it works, if we go back to our LSM tree, the way it works is that a tombstone actually is treated as just another key value entry. So we insert the tombstone for 5, we set it into the memory buffer, we treat it as another key value entry. When the buffer is full, we push it to the LSM tree as normal. And now this means that logically all the previous versions of 5 are invalidated, but they do exist in the tree. Right? They do exist in the tree and they occupy space, but they are not accessible to the application layer anymore. If I have a query on a deleted entry, what will happen is that the deleted key, the tombstone for the key value I'm deleting will be inserted into the Bloom filter just as another key value entry. So my Bloom filter would say, yes, I have 5. I will use my metadata and I will find 5 on the disk to only to find the tombstone for 5 and say, you know what, I read something from the disk, which is the tombstone, so I'm stopping here. There's no need to move forward. Now, what are the problems that this might cause? So the first problem is that it's a performance roadblock as well, not only about privacy. So what do I mean by that? If I have my tombstone for 5 here, and I have all the invalid entries, and I have maybe other tombstones as well, I simply have space amplification because I'm using space with invalid data that I cannot do anything useful. I cannot make anything useful out of this data. Number 2 is that I'm moving during compaction, I'm moving data, and I'm moving also invalid data and possibly also tombstones without getting rid of them. So presumably I'm doing the writes of invalid data that I really didn't need to do if I knew better. And last but not least, all the tombstones and the deleted entries, as you can imagine, they remain indexed and essentially in our like they occupy space in our Bloom filters and our metadata in order to be able to accommodate every query. So they pollute, so to speak, the metadata with information about invalid data. So this is leading to somewhat reduced read performance. In fact, state-of-the-art system that handles deletes like the ones I mentioned before, they do face all these problems, and for them, deletion is a problem. Now, there's another problem which comes from the privacy aspect of things, and comes with whether we can offer a guarantee as to how the data will be deleted. Note that in order for the data to be permanently deleted from the LSM tree, the tombstone has to go through the whole LSM tree and reach the last level to guarantee that upon every merge, it goes this completely purging the prior entries of 5 key in this case, right? However, this might not happen. We don't know how fast it will happen. In fact, this depends on a number of different things that we don't always control as a system engineer, on data movement policy, ingestion rate, the number of levels in the tree, and the growth factor, so how fast data is coming in. And we can have scenarios where you know what, this tombstone might move on to the next levels naturally, quickly enough, but then some other cases it might just stick to that level because we have a lot of updates, right? And then maybe if we have a DTH overall, threshold, maybe we will exceed this threshold because we will be moving other files and not the tombstone file as fast as we would like to do. So instead, in order to address this, what we did, and in order to avoid the potentially unbound delete persistence latency, what we did is that we introduced a new compaction strategy called fade that essentially changes the compaction trigger and the compaction data movement policy to be a time to live assigned to every tombstone upon inserting a tombstone. And similarly, the tombstone density and the tombstone age is the compaction data movement policy upon merging. Now we implement this RocksDB level DB, and let me very briefly go over the high-level idea of how this works. So if the application has a maximum threshold DTH that needs to guarantee that all the entries are deleted in that time, are physically permanently deleted in that time, what we do is that we take this time and we divide it into L-1. So if L are the levels, L-1 intervals with exponentially increasing size, and we guarantee that every tombstone that is inserted in every level has to be moved on to the next level with the corresponding D1 mini threshold. So if we have a tombstone here and it so happened to be moved to the next level before the threshold, so be it. It's great. We move on to the next level, and we of course purge any invalid entries of that level. Now, if it so happens in level 2 that we just are reaching the threshold D2, then and the age of the tombstone is exactly reaching this threshold, then we're actually selecting this file and we are pushing this file to the next level to guarantee that overall we would not go above the threshold. The same thing, you know, is repeated in the next few levels. So that way we guarantee that within DTH amount of time, we push the tombstone in the last level of the tree. And when this happens, we know that there's no invalid entries for that tombstone in the tree. And of course, we don't need to keep the tombstone anymore around because everything that was there has been already invalid, has been already paired from the data. This might lead to ties in practical workloads. For example, we might have multiple files with tombstones or multiple files with expired tombstones. The way we break the ties is that we go to the higher level of that contains expired tombstones, and then we select this file. If we have only in one level, then we select the file with the most number of tombstones. In terms of, I have some result graphs that if we have the time, I would like to share just 2 or 3 slides. And okay, great. And then we can actually wrap this up and discuss any comments or questions you might have. So in terms of results, so here I show on the x-axis the age of files that contain tombstones, and on the y-axis the distribution of those files. So essentially, point here means that you know, we have 10 files that contain tombstones of that age, right? So the gray area here is the CDF of the state-of-the-art system without any delete specific compaction strategy. And here the other 3 colors correspond to our strategy while we were setting a delete threshold as indicated by the dashed lines here. So the green line corresponds to the green, to the blue line, to the blue area, the green to the green, and so on and so forth. So we clearly see that there is no tombstone that is above the age threshold that we said. And the next question is, at what cost this is happening? In fact, we have more performance benefits. Space amplification wise, anytime we are actually getting rid of data faster, we have less space amplification in the end, like on average in our workload, because we do not maintain all these invalid entries, which is a huge win. So we see the space amplification reduced by 2 to 10x. Now, interestingly enough, we also show that read performance-wise, we have a benefit, and this comes from the fact that we have fewer data in the tree, because remember, every key value entry and every invalid key value entry still occupies space and still occupies metadata space. So we actually had a performance improvement of 1.2 to 1.4x in terms of read throughput. And our initial experiment in terms of write amplification, so how much more writes we're doing compared to the baseline, showed a 4 to 25% increase in terms of write amplification, which, however, as we observed with more experimentation, is amortized over time. So if we keep using our strategy for days and days and days, we observe that the amortize the overall rolling essentially, like with an increasing window, write amplification goes down to a very modest 0.7%, because essentially we are moving less invalid data. So even though in the beginning we had to move data to get rid of the first generation of invalid entries, as we keep moving that, as we keep doing that, overall we've been moving less and less invalid data. So we win by having smaller data, smaller trees essentially, and leading to smaller write amplification overall. And there might be a question that I don't have a slide about, and the question might be, okay, how important it is based on these regulations to have a threshold? And if someone has read these regulations, the threshold can be 30 days. So how difficult it is to actually delete things in 30 days? In fact, we were motivated exactly because it was not feasible to delete data in 30 days. That's exactly what happened when we reached out to industry, people from many major big companies that we are actually quoting in some of our papers. They did say that they needed to perform a forced full tree compaction every 2 to 4 weeks in order to be compliant. And this actually led to significant performance problems in terms of huge latency, huge compaction latencies that they wouldn't have otherwise. So in fact, it is indeed a very practical problem. And we're hoping with this work, which is done on top of ROCs, to be one of the systems that actually faces these challenges, that it will actually make their lives easier. To connect this work with the previous discussion, essentially FADE is a new compaction policy that answers these 4 questions with a leveling data layout, a file compaction granularity, an expired tombstone TTL, and the least overlapping parent as a second strategy for the data movement policy, and the tombstone age with level saturation as a compaction trigger. Okay, so so essentially that is putting together the two and showing how we can keep building new compaction strategies to solve specific problems. Here we address the delete problem, but we might have more down the line. So this concludes the second part and probably the talk for today. Let me very quickly thank all of my collaborators and sponsors that we have been working on these projects together. And of course, thank you for your attention. So here you can see all of the students and postdocs and collaborators I have, our sponsors, and I would like to thank you for your attention.